How are the homeworks going? I think there was a homework that was already due, right? Did you? I checked my mailbox. Did you guys submit there?
Yeah, I submit. I put there.
Okay, so that's taken care of, then, right?
I'll put it in later.
Okay. I posted a relatively smaller homework so that I can make it due on Tuesday itself. Again, if you feel that it is too short a time, take your time to finish it on, let's say Thursday also. But I will assume that this is due and that next homework will be in that as a reference point. From there we have so we started relativity, which was motivated from the fact that we have a constant speed of light, which immediately led to the idea of principle of relativity. And there, what we said is that there are quantities that transform under Lorentz transformation in a specific way, like position and time. Together is what is important. Position itself might be different in different frames, and time might be different in different frames. Same thing, we did it for velocity, acceleration, force. So all these quantities we could find the respective components which do that. And then immediately we say, what about electric and magnetic field? What about the electromagnetic quantities? Right? We would like to at least find the pieces that go together. So that's our goal. So let's look for let's go back to Maxwell's equations. That's equal to del dotted with E, and that's equal to rho over epsilon naught. And let me write that as 1 over epsilon naught times rho. That was one of the equations. Then we have L dotted with B is equal to 0. Right. And then I have L cross E is equal to minus U dt times B. And we have L cross H, which can be written as B, right? Let's write it in terms of B is equal to, now it is time derivative of epsilon. So there is a mu there, there is a mu coming from this side also. I want to write this as mu naught epsilon naught times d by dt E plus mu naught times J. Typically, I think earlier we have written this mu naught in the magnetic field and called B over mu naught is equal to H. And so we also have epsilon naught times mu naught is equal to, what is that equal to? In terms of speed of light,
C square.
1 by c square, right? No, so 1 over c square. And that allows us to think that, oh, okay, so these two are not independent, right? I can replace one with the other. So let me replace wherever there's an epsilon naught with, so I'll have mu naught everywhere. So let me write this as, so multiply by a c here. So that gives me a c here. And no, that's not what I want to do. Oh. I want to not do that. I want to write divide by c and then divide by c here. Right? And if you notice, c square times epsilon. So mu naught is 1 over c square times epsilon naught. So if I put in one more c square, that helps. So I'll put one more c square. I don't want to manage a c there, so I'll give the c to rho. Thus you'll see the motivation there. And c square epsilon naught is mu, so right, this is mu. So I've put the c with the rho and c in the denominator of e. We have already seen that c goes with time all the time. So let's give that a c here. And that gives us c here. And divide by c if you want. Epsilon naught mu naught is nothing but 1 over c square. So give one of the c's to T and one of the c to electric field. And mu naught we said we can keep, right? So everything is written in terms of mu naught and c. And we distributed the speed of light in a particular manner. Okay. That's good. And we also remember in relativity that x alpha is equal to c times t and the vector x. And x subscript alpha is minus ct. X, this is for reminding ourselves, yes, no. And we now have to define what about d alpha. So this is now derivative. Now derivative is defined as the spatial part is the gradient itself. And the time part is the derivative with respect to time, but now with respect to t, and then there is a c there, just for dimensional purposes. Notice when it comes to position, it is the superscript that is chosen as positive. When it comes to derivative, it's the subscript that is chosen as positive. And d alpha is minus 1 over c d by dt gradient. Okay. What is x alpha? So if I take derivative of alpha times x beta. So that's an operation I can perform. So I start from here. I can take the 0th component of this and operate on the 0th component of that. Or I can start with 0th component of this and operate on the first component of that. And so on. There are 16 possibilities. For here, for there, the 16 derivatives possible. And they will always, so this will give us, if they are the same, it is 0, oh sorry, 1, otherwise it's 1. And that's defined as delta alpha beta. That's your Kronecker delta in 4 dimensions. Okay. What about the alpha x beta. So I start from here and operate on this. So start from here and operate on this. Again, just because of this, the same structure here, all of them are zeros except when t hits the t, x hits the x, and so on. But when t hits t, it is a -1. It is not positive. So this is equal to -1, 0, 0, 0, 0, 0. And that's what is defined as G alpha beta. We'll call that. It's almost the same as the metric. Almost the same as the Kronecker delta, except that the time component is negative. In the same way, you'll have the alpha x beta will be equal to -1, 0, 0, 0. Now that's G alpha beta. That's just whatever we did earlier, at least for the position case. This is a simple notational thing. So this is often you say this is index relations now in 4 dimensions. Earlier we worked in index quantities in 3 dimensions. This is a 4th in Minkowski space, in the sense that this up and down matters. Right? We change. Okay, with all this, let's proceed. Yes, so this is called a contravariant vector.
This last one, last matrix.
This one?
Minus same.
Yeah, this is same minus. So this is minus, that's also minus. These two are exactly identical. In fact, if you multiply these two, you get that. So there is also this relation that if I do G alpha, let's say mu, and G mu beta, whenever there is one up and one down and it is being summed up, this is like matrix multiplication of these two. Right? Then you get delta alpha beta. So this is the inverse of this. This is the inverse of that. And 1 over -1 is -1 itself, right? So in that sense. Okay, that's okay. So let's define certain quantities. We want to now write this in a covariant form. So what we are going to do today is that there is no new physics that is going to come out of it. So notice that whatever we did in special relativity, there it was a little deeper in the sense there was one point where we defined momentum as m times v times gamma, right? And the energy as m times c times gamma. After that, it was mostly putting things together in the right manner. Right? There is no new laws that we came up with. It's only we modified the same old everything stayed together. We saw that momentum and energy go together, force and power go together, and so on. Right? We saw connections between quantity, position, and time go together under Lorentz transform. Same thing here. Most of everything is going to stay the same. It's just that we're going to put Maxwell's equation in a covariant form, that's the language, in a manner in which the relativistic version or form for it comes out very cleanly. And all this will be compiled into 2 equations. All this will get into 2 equations. So the idea is how these things go together. So let's define some quantities. So let's call for current. We have defined for position, for velocity, for current will be J mu. Let's call it J alpha because mu is mu naught. That's relatively. So J alpha, we will say is C times rho, and this is the usual curve density. or current density. Same old current density, charge density, but we put this together, C times rho and J, it's like position and time. Then we call for vector potential. Remember, I should remind ourselves that B is equal to del cross A. And electric field is equal to negative scalar potential minus A by dt. That's your electric and magnetic field. So then you ask, how does this potentials go through? We define A alpha, say this is phi over C, and the vector potential. Okay, so the scalar potential and the vector potential associated with electric and magnetic field, they go together in electric field. Again, what does that mean? It means that in one frame, you could have, you could measure A and phi. If you go in another frame, both will change, but their magnitude, the Lorentz vector associated with it, that will remain the same. Okay, so that's good. And our goal then is, what about electric field and magnetic field, right? That's of interest. And you say, where does that go in? So the two vectors now, right? They don't fit into these kind of structures. So it will turn out that that's a tensor. So let's define. So this is called the electromagnetic field tensor. Will be defined as F mu nu, or the F alpha beta, be defined as the alpha A beta minus of the beta A alpha. That's just a definition now. And it will turn out that electric field is there inside this. Okay, so that's our goal. We want to recognize this structure. It's clear from one, just by construction, that if F alpha beta is this, then F beta alpha is equal to B beta A alpha minus B alpha A beta, which is exactly negative of F alpha beta. So it is antisymmetric. So if it is antisymmetric, that means that it has the form of this kind. So if this antisymmetric, immediately tells us that F alpha beta has the form 0, because if this is minus of that, that cannot be the 0th term. So that's, and then we have F01, F02, F03, 0, F1, 2, F13, that's 0, and F23, and that's 0. Once we know that, since it's antisymmetric, I can immediately write the rest of it. So it's minus F01, or I don't have to say that. Like these will be identical in a sense. F10. F10 is minus of F01. This is F20 and F30. This is F21, F31, and this is F32. This is non-independent. There are 6 pieces here, right? The independent pieces are 1, 2, 3, 2, 3. This will form one vector, like 1, 2, 3, 3 components of a vector, and this will form the other 3 components of the second vector. It'll come out that this is the electric field and that's the magnetic field. That's what is going to happen. Okay, so, or if I were to just give you the message beforehand, so is it, right? So I'm going to show this. We're going to see that this is 0 electric field. So this will be E1 over C actually, E2 over C, E3 over C, 0. This will be B3 minus B2. That's a vector, but it's not coming in the right form, right? It's a minus sign there. And then there is B1, 0, and that's it. And once you know that, you can put the opposite, the negative sign of that. Negative, negative, that's an antisymmetric. But how did I get this? So this was just a definition. So let's see what this is. Okay, so let's evaluate each of this separately. Any questions at this stage?
Now, how can you tell that this one is for electric field and another one is for?
I don't know. I just put a question mark. I'm going to shift. So this is not at all obvious. Since I mentioned that as a vector, like I shouldn't have put that at all. So we know only this much till now. I defined this, that's done. Right? So we don't know anything. So if you want, you can erase this. Right? If you want, just have a feel that in your head, because motivation also helps, right? So I'm going to show that this is an electrical magnet. We don't know anything about it. So here is that, let's look for what is that 0, 1 then, right? So let's say instead of F01, let's call it F0I. Right? So I is 1, 2, 3. So I have 3 components to this. By definition, this is B0 AI minus BI A0. Is that clear? That's fine. That's the way I construct or definitely define this. But what is D0? That's the 0th component of my derivative operator. It's superscript, so it is minus d by 1 over, right? Minus 1 over c d by dt. Right? That's because I'm using here. AI, that's superscript A, that's A, vector A. Right? That's vector A. Okay. And since I'm writing it as a vector, so this is kind of unnecessary, but I'm writing a vector and an index just to point out. Since we have this electric field. So it seems like this is showing up here. This is gradient, superscript E, that's a gradient operator. So it's minus of gradient operator. And A0, the 0th component of the superscript vector potential, that's 5 over C. So that's 5 over C. And then you clearly see that, that's nothing but 1 over C times the electric field. Right? That's how I know that that's a. So the 3 components on the top of that, so this is the tensor, that's actually the electric field. Next, of course, we now need to know what is the rest of the 3, and I'm saying that's a magnetic field. So let's say this time what is Fi J, right? Where I is 1, 2, 3 and J is 1, 2, 3. Okay, so this is the spatial part here. So we're talking about this piece. So 0th part we have taken off. So that's equal to I J minus J. Same idea. So this is gradient. So now this is a tensor, right? So there are 2 vectors in there. So let me write that as del I. Aj is nothing but the vector Aj, right? The same thing. This is now vector potential J, and this is minus dj ai. So what is that? Remember your B is del cross A, right? So how do we read that out? B is del cross with A. And how would you write that in index notation? You would say this is B of K is equal to epsilon K ij del I aj, right? That's how you would write that. But how do you see this coming out of this? That's not very clear. So what you do is, okay, how do I make this work? So there's I and a j there. That's I and a j. So I multiply by epsilon k. So let's do that. So I do epsilon k, maybe denominator, maybe epsilon k I j. Maybe before that, let's do it small. Right? Let me bring this all down. That should be fine. Since it is all spatial piece, doesn't matter, nothing is going to change. So that's the same as del I aj minus del j ai. Only when the time piece comes, I have to worry about the sign changes. Multiply this by epsilon k ij and f ij. That's the same as epsilon k ij and del I aj minus epsilon k ij del j ai. That's my cross product. That's my magnetic field. That's equal to del cross A, the kth component of it. And what about this? This I have to change now. I'd write J and I, right? I have to swap J and I. That will change this. So that makes it a plus. And again, a del cross A of K. That's the same. So that's two times magnetic field, right? So it's 2 times magnetic field K. Okay, but that still doesn't give me what is Fij, right? So we were interested in this Fij. It seems like, okay, I see the connection with the magnetic field, but not very clear. So what you do is, okay, so let's again multiply with this with something so that we get Fij alone. So what I'll do for that is now once we have reached this state, I put in an Fk. So I multiply this with Fk Mn. And Fij. So that means that this is 2 times epsilon k Mn times Pk. I'm trying to get the Fij out, and this seems like I'm going farther and farther from it, but it will come out that this will help. Okay. This is an identity, right? We know this identity for, let us say we have symbol. So this is delta Mi delta Nj minus of delta Mj delta Mi. times f phi j is equal to 2 times epsilon k and n k. This simply replaces m and n. So I have f m n from the first term, and the second term is j gets replaced with m. So it is f n m is equal to 2 times epsilon k m n times dk. These two are the same because this is antisymmetric. So I have 2 times Mn is equal to that. The 2 cancels out. And what I learn is that so Fij or Fmn is equal to epsilon m and k times dk. That's the, and that tells us that is if it is F12, then it is 1, 2, 3, the third component. So the third F12 is the third B3 that comes in. So, so this tells us that F12 is equal to B3. F23 is equal for F13. So F13 is equal. So 1, 3, 2. So I have stop this. So it's minus B2 and F1, 2, 3 is equal to B1. Clear? Any questions at this stage? So all this tells us that F alpha beta, it's very clear now that this is 0 electric field, the first component of that with respect to C, E2 or C, E3 or C, 0, E3, no C in here, so it's minus B2, 0, E1, minus E1, C, minus E2, or C, minus E3, or C. Again, what was the motivation for doing all this? Main thing is that position and time under Lorentz transformation, if you have 2 different frames, they will measure distances differently, time differently, but there is an invariant quantity between them, right? C square, T square minus X square stays the same, right? So what we have now seen is that, oh, they will change, electric field will change, magnetic field will change, but then what remains the same? We would be interested in asking what exactly remains the same in electric and magnetic field. What should I measure which will be the same irrespective of who is moving around with respect to each other? That, if you see, this is a tensor, and under a Lorentz transformation, since there are 2 indices, there will be 2 Lorentz matrices that will multiply. That's like saying, so if you say under Lorentz transformation, how does this go? So this is F prime, right? Let's say F bar alpha beta. How does that transform? So let me write this symbolically, not with the details in there. So F bar, how will it look like? Since there are 2 indices, this will involve L, F, this is the Lorentz transformation, and there is an L inverse that comes in. Okay, that's how a tensor rotates or transforms under a Lorentz transformation. A vector transforms as L times a simple matrix times the vector. A tensor of second rank will have 2 Lorentz matrices. If it was a tensor of rank 3, then you'll have 3 such matrices. But this is also a similarity transformation. So then you say that, oh, under a similar, so Lorentz transformation is nothing but a similarity transformation. And what remains the same under a similarity transformation? And then you realize that, oh, it's the eigenvalues. And what are the eigenvalues of F? Because that will remain the same in all the frames. And it turns out that the eigenvalues can be constructed out of, they're not exactly the eigenvalues, but they can be constructed out of what is Lorentz invariant is E square. And this is going to be your homework. Show that, or yeah, since it is a homework, I don't have to tell this. Yeah, so yeah, this is yeah, you have this part of the homework. I don't have to tell it like this. If X alpha is a Lorentz vector, 4 vector, what remains the same in between frames? Not X, not time, but what remains the same? That's velocity or position.
X alpha dotted with
X alpha. If this is what you're talking about, X alpha is Lorentz invariant. Right? So if you measure X alpha, it will be the same in every frame. Now I have F alpha beta. What should I get for that? So you have to do F alpha beta. They construct a scalar out of it. F alpha beta. If you do the square of this, this will be invariant and not depend on any frame. And then the question comes, what is that equal to? That's your homework. Basically, short from your F00, this is summation, right? You have to calculate this and you have to show that this is nothing but E squared minus C squared B squared. That's it. And actually, I have to show that that is C squared. Okay. So what that means is that in one frame, you go and measure electric field. Let's say in one frame, you measure this to be a positive quantity. In every frame, that has to be positive. That means the maximum I can go is that E is there, B is 0. So what that implies is that if E squared minus C squared B squared is greater than 0 in one frame, then there exists at least one frame in which B is 0 in a frame. Because if B is 0, I still can have that 0. But I cannot switch it. I cannot have pure. If in one frame it is pure electric field, I cannot make it into a magnetic field. The electric effect has to remain an electric effect. I cannot make it into a magnetic effect because this has to stay. It's the same, correct? This is the same everywhere. If it is positive, it has to stay positive. It cannot switch side. Okay. If this is less than 0 in one frame, then E is equal to 0 in a frame. A means that it exists a frame in which electric field is 0. That means it is purely magnetic. Right? You can convert that into a magnet. And then there is one more condition, right? E squared is equal to B squared. And when, give an example of a case when E is equal to B, a plane wave, right? Electric and magnetic field is the same. And if it is in one frame, then it has to be the same in every frame. That makes sense because that's light, right? The plane wave was light, is nothing but light. If light looks the same in every frame, And because Y has this property that is consistent, then E is equal to C times B in every fluid. So that's an invariant. Okay. Okay, that's good. So that was a distraction a little bit that okay, we went ahead and did this and you show this in your homework. Okay, but that's if you have this, then what is your Maxwell's equation? Correct? Let's try to do this. So let's try to do something now that we have this information. So our write this down. So F0I is electric field EI over C, and Fij is equal to epsilon ijk dk. Since there's a space, it doesn't matter going up and down. Let's do F alpha beta, and I multiply this by a derivative of F alpha beta. Is this a vector or a tensor? Is this a scalar, vector, tensor?
Tensor,
Alpha is summed up,
also vector.
so it's a vector or tensor of rank 1, which is a vector. Right? So it's a vector. So let's see what this is equal to. Since it is summed up, so it is D0 F0 beta plus DI Fi beta. Right? I would go from 0 to 4. I kept 0 separate, and 1 to 3 I put it in I. That's the way of saying that. If one of them is 0, then beta has to be space like, right? So this is B0. Yeah, so how about this? Let's say if beta is equal to 0, there is no information, right? Or is there any information? Yeah, let's say beta is equal to 0. Yeah. First, let's say beta is equal to 0. Then this is nothing but D alpha F alpha 0. Set beta equal to 0. And this is D0 F0 0 plus DI Fi 0. Is that clear? F0 0 is 0, as that doesn't exist, so that's 0. DI is plus DI. Fi 0 is nothing but electric field here, but it's minus of the electric field, so it's minus of the electric field over C. Right, so this is equal to del dotted with E, right? So this is minus 1 over C, or right, this is minus del dotted with E over C. Right. I'm just reading out this piece for beta equal to 0. The zeroth component of this vector. The zeroth component of this vector, del dot E, is del dot E over C is max using Maxwell's equation. That's mu naught times, that's minus of mu naught times C times rho. Good. So your first Maxwell's equation is contained in this part, but we have to put this all together, but let's wait. This is only beta equal to 0. Let me do beta equal to I and then come back to that. Okay. Any questions? So mostly mechanical. Beta is equal to, let's say, I now. So d alpha f alpha I, that's equal to d0 f0I plus dj fj. I cannot say I here because I have been already used. D0 is nothing but time derivative plus 1 over c d by dt. F0I is nothing but electric field I over c, and this is plus gradient of j. Fji is nothing but minus fji is epsilon jik dk. Okay. So that's the same as 1 over c d by dt of electric field, say electric field EI, right, over c, and this is minus, correct? So this is minus of, since if I want to write this as a cross product, so this is j and a k, so this is minus of del cross d, and this is the ith component of that. And if I use Maxwell's equation now, Maxwell's equation tells us this minus of this will be minus of mu naught g, right? So that's the same as minus mu naught times j I, if you want. So this was a vector, right? D alpha f alpha beta. So what we can say is that the d alpha f alpha beta, if I put beta equal to 0, beta equal to 0, then this seems like I have this is equal to minus mu naught c rho. If I put beta equal to I, right? These are the 4 components, first component and the 3 component. If I put beta equal to I, that's minus mu naught times ji. That seems to suggest that I should put this together. Right? That's the motivation in defining my 4 current density like that. So my Maxwell, first 2 Maxwell's equations are nothing but, so this is equal to mu naught minus mu naught times j beta. Right? This beta is a free index. So my Maxwell's equations are, my Maxwell equation is, 2 of my Maxwell's equation is d alpha beta is equal to minus mu naught j beta. A very compact form of writing Maxwell's equation is 2 of the Maxwell's equations, this one and this one, whichever has a current and a source, current and charge in it. That's these 2. So the 0th component of this is one of the Maxwell's equation. The vectors I beta equal to I is the second Maxwell equation. One is scalar, one is vector, right? Scalar, vector. Okay, clear? That leaves us with the question, what about these 2? Right? Where does these 2 equations show up? And that leaves us, okay, so there is a tensor here. Let's work with the, let's manipulate this tensor a little bit. But before I go ahead, I should ask you guys the questions. Okay, so So to look for the other two Maxwell's equation, we now construct another tensor. We construct another tensor very closely related to the current tensor. This is called a dual field tensor. That's F tilde alpha beta. Well, let me put it downstairs. So subscript alpha beta will be equal to 1/2 epsilon alpha beta mu f mu nu. That's a Levi-Civita symbol in 4 dimensions. Like we have constructed Levi-Civita symbol in 3 dimensions, and that was defined as there was epsilon ijk, right? What does it mean? It is equal to 1. So epsilon 1, 2, 3 is equal to +1, right? And any combinations of that, any swapping, any one of the swaps will give you a negative sign, and plus cyclic components. And whenever there is a repetition, that's equal to 0. The same idea goes through here. So epsilon alpha beta mu nu is defined by starting from epsilon 0, 1, 2, 3 is equal to +1. You start with this, and then every time you swap, you get -1. And notice here it was always cyclic in the sense 1, 2, 3, 3 to 1, so all were positive. That need not be the case here, because here, since it is 3 of them, whenever I swap, I reach a case where 1, 2, 3, 3 to 1, they will all look the same. But here, just because 0, 1, 2, 3 is positive doesn't mean that 1, 2, 3. So for example, 1, 2, 3, 0, right? That seems cyclic. But what is this equal to? To get from here to there, I have to go 1, 2, 3 times. Like 3 swap I have to make. 0 and 1 swaps, then 0 and 2 swaps, and 0 and 3 swaps. That's equal to -1, even though it is cyclic. So I should say cyclic swaps. Like cyclic. Or what do I mean by? Let me just say plus swaps, right? Let me not say cyclic at all. Okay. Okay, so that's my definition. But then what is this equal to? F alpha beta. What is that equal to? So let's investigate that. So again, the same procedure, right? So we start from F. It's clear that 0, 0 is 0 because it's antisymmetric. So F tilde 0 I. Let's see what that is. That's equal to 1/2 epsilon 0 I, and that is mu nu, but now mu nu cannot be 0 because that 0 is already taken up. So this is j k and f j k. If this is fixed 0, ijk has commutations between them. So that's nothing but ijk itself. So this is 1/2 times ijk fjk. And that is equal to epsilon ijk. Fjk is that correct? So I gotta put this in. That's ijk. Fjk is epsilon jk, and now I put m, right? M. That's using this solution. I can keep it upstairs because this is all spatial. Then you use the identity here that, oh, there's jki, so this is equal to 1 by 2 times 2 times, that's an identity I'm using, km times pm. 2 cancels out, delta km, so that's p of k. So let me, oh, why did I lose my index? So jki, right? So this is, right? So this is not identity, so this is delta im. And Bm. And this is Bi. So a lot of index notations being used, and you will need all this in your homework. Right? You'll be doing pretty much the same, but it's only like you will basically be proving this, and there are 2 more. So I've shown that f alpha beta now, f tilde, the dual tensor related to this. So let's say alpha beta downstairs. That's equal to 0, B1, B2, B3. Which makes this minus B1, minus B2, minus B3. And we of course know that this is 0, 0. And this leads to the idea that what is this piece in here? And it will come out that that's electric field. So basically electric and magnetic field are kind of getting swapped in this construction. Any questions? Yes.
So for the Levi Civita there, the EIJK, you have like a superscript and subscript for the indices?
Yes, here, right?
Yes, yeah.
So you would like it.
I'm just kind of getting confused on the like implications. Like,
Okay,
is there a
so how
difference?
about this? One should be, if you want to be strict, this should be here. Does that help? Okay, that's better. Like then it is consistent. But why I made that switch is that if it is a position space, then up or down doesn't matter. It's only when the time component comes in, it comes with a sign. And since I for some reason wrote this upstairs, I was using that. So if you want to be, I think it's a good practice to keep the summation indices 1 up and 1 down. That's a very good practice. And but it's just that when you're completely in the space part, it doesn't really matter. So I use that fact, but let's be consistent and stay in that way. Good. Any other questions?
So you mentioned that here it is swapped.
Yes.
How can you explain?
I have only shown that F0i is this, correct? In fact, again, let's stick to the, this is up, down, right? This is 1, 2, 3, 1, 2, 3, right? I have shown that this is equal to this, so this is the thing. So surely the electric field gets replaced by magnetic field. I haven't yet shown that this is electric field. I'm going to show that this is going to come out with the electric field, and then it is swapping, right? You've changed electric and magnetic field. It seems like you get the dual tensor. Is that clear? So that's what I meant by that. So we are to show now what is the ij component of this. That's all. Right. So let's show the ij component of this. So f, the dual tensor Fij is equal to 1 by 2 epsilon ij. So this is now space, and alpha beta and or mu nu f alpha beta. Great. a purely space-like. I and j are either 1, 2, or 3. There is no 0 in there. So this has to have a 0 because they have to be all different, right? Levi-Civita symbol, the definition is that all the index has to be different. So if 1 is here and 2 is here, these two has to be 3 or a 0. If this is 2 and this is 3, then this has to be 1 and a 0. So 0 is surely available. So let me put that down. So that let me use that fact. That's 1 by 2 epsilon ij. This is a summation here in alpha and a beta. So first let's sum over alpha. So this is 0 times beta and f0 beta plus 1 times 1 by 2 epsilon ij 0 times 0 and a k, right? So let's say k times beta fk b. Right. So I summed over alpha. And next, let me sum over beta. So that's epsilon ijk 0, 0, f0, 0. I'm doing this plus 1 by 2 epsilon ij 0. I have k available here, so that's k f0k. This is remaining 1 by 2 epsilon ijk 0 fk 0 plus 1 by 2 epsilon ijk. I have a fourth, and that's ijkm, let's say fkm. So clear? It's just expanding out. Let's begin with the last piece. ijkm, they are all spatial. Right? The way I constructed it, this is 0 is already taken over here. So m is space-like. K is space-like. I and j are space-like. So at least one of them is repeating. I have 4 index, but only 3 availability, right? I 1, 2, or 3 if it is space. So this has to be repeating. If it repeats, epsilon is 0. Like Levi-Civita by construction is whenever they repeat, whenever the index repeats, it's 0. So this is 0. No choice. Next, this is repeating, right? 0 and 0. That's 0 again. Great. Let me move this 0 to the first. So this is 2 times switching, right? 0 goes to 0. So this is equal to 2 times swap. So that's 1 by 2 epsilon 0 ijk f0k. And this one I have to switch 3 times. 1, 2, 3. Right? So it's minus 1 raised to 3. So it's plus 1 by 2 times minus 1 raised to 3 of epsilon 0 ijk. And I have another swap with k and 0. Let me swap k and 0. So that's f0k with a minus 1. That makes exactly this, because this is minus 1 and minus 1 raised to cube. So that's 4. So this is 2 times. This is 2 times. Or 2 times 1 by 2, 1 by 2, it's 1, right? So this 0 ijk f0k. Epsilon 0 ijk is nothing but epsilon ijk itself. Epsilon ijk f0k was electric field. So that's epsilon ek c. So the first component, or when I and j is 1 and 2, that's 3. Right? So this means that this is, and this again doesn't matter if it is up or down. So I'll write this as B, or sorry, E3 over C. This is minus E2 over C, and this is E1 over C. That's the anti-symmetry that is deciding that. That's because of this. And that's equal to, this is minus E3 over C, E2 over C, 1 over C. Now that we have two tensors, earlier we constructed this times this was an invariant. Now that we have two tensors, we can construct more tensors. Right? So there are two more things we can construct, and that is I can also construct, let's say, let me build this here. So C squared F tilde alpha beta times F tilde alpha beta will also be a Lorentz invariant. So if I want to measure, it's not only this, I can measure this also, right? That's also will be a Lorentz invariant, and it comes out to be the same. So it comes out to be the same, so it's not interesting. This is also a Lorentz invariant. But what if you multiply these two separately? So what if you multiply F alpha beta and F tilde alpha beta? That's also Lorentz invariant, and this time I multiply only one C, and this comes out to be equal to minus B dotted with E. That's interesting because B and E change in different frames, but their dot product is invariant. That means that if it's an acute, if it's making an acute angle in one system, one frame, in every frame the angle might change, but the scalar product remains the same. Right? So if it is acute, then it has to remain acute. If it is obtuse, it has to remain obtuse. And if it is zero, which is the case in the case of light, right? Light is electric and magnetic field is zero, that's invariant. That has to remain zero all the way. If it is perpendicular, it is perpendicular in every. Right? So that's interesting. So these two are the invariant quantities. So all this was to develop it. What you want to keep in mind if you're doing experiments is E square minus C square B square is frame independent. E dotted with B is frame independent. These two are special quantities. If you want to measure distances or measure quantities, you measure these two and they will remain the same. That's the content. But now we still did not get the two Maxwell's equation, right? We constructed the heat tensor. Let's construct. We have to have F alpha. So now let's do the alpha F tilde alpha beta. Oh. Okay, what is that equal to? Let's do beta equal to 0 first. You have the alpha F tilde alpha 0. So that's equal to D0 F tilde 0 0 plus DI F tilde I 0. Right? That's equal to 0 plus DI is gradient of I. F tilde I is nothing but magnetic field. Right? So that's BI. But we know that that's equal to 0. So that's equal to del dotted with B. But that's 0. Right? So the zeroth component of whatever vector we are talking about is 0. What about the space vector? What if theta is equal to I? Then it is the alpha F tilde alpha I. That's equal to D0 F tilde 0I plus dj Fji. This is 1 over C d by dt of electric field, no, magnetic field dI at F0I plus del J Fji is F tilde Ji. F tilde Ji, we said F tilde Ji here, epsilon ijk. It's epsilon J I K E K over C. That's the same. as 1 over c d by dt of magnetic field plus del cross k, like j at jk, so that's del cross k. Why am I off by a sum? Let's tell that. Okay. J by k, right? F j by j by k. Apparently, so this is coming this side, so this is minus of k at top. And what is wrong? F e 0. 0 was up, F tilde 0, right? Oh, this is upstairs, right? This is, oh, this one is the negative sign. This is upstairs. What we showed here is downstairs, right? F tilde. This is a negative sign. This is negative, that's negative, and this is the fourth Maxwell's equation, that's equal to 0. Because of the Maxwell's equation. This was an error here. This was a negative sign, that's 0.
And this on the other side too.
No, here it's because space, right? It's all space line, so no problem. So what that means is that the zeroth component is 0, the space part is 0. The alpha, the other Maxwell's equation is written in terms of the dot tensor is exactly 0. I was supposed to move this thing. Yes.
We have del cross E over C raised to the K. This is supposed to be I.
Yes.
For your matrices.
And what?
Oh, and for the matrices on the right side of the board there, you have the bottom row, third column. Should that be negative? The bottom row, third column.
Oh. Yes.
It's the same for the.
Oh, I meant those.
Yeah, I just didn't know if that.
Thank you. Good observation. If you make consistent mistakes, then you almost think that.
Yeah.